I'm in a new place here, and you can see that the lighting is a little different, but I hope that doesn't change anything. We've been looking at methane, its budget, its emissions, its relations to wetlands, impact of climate on wetlands and wetland distributions and climate, as well as methane glut rates. The last piece of that puzzle in this kind of survey of feedbacks is, of course, methane and carbon dioxide feedback mechanisms. This is a schematic that's showing the climate methane feedbacks, and the letters A to D are discussed in the text as we saw before. Effect of methane on climate as a greenhouse gas, very strong greenhouse warming potential. Effect of climate on methane emissions by increasing rates of decomposition and influencing wetland context. The CO2 fertilization effect on wetlands, and melting of permafrost, increasing the inundated areas in the northern seas. Okay, so look at this again a little bit. We have CO2 anthropogenic emissions coming into the system on this side of the CO2 cycle, and we have methane anthropogenic emissions from rice paddies, cattle, various other artificial sources we have created in terms of additional methane, for example, and fossil fuel extractions, leaks from there, etc. So CO2 in the atmosphere is going to have a fertilization effect on photosynthesis and vegetation, providing a terrestrial carbon sinks. We already talked about the limitations imposed by availability of nitrogen and so on. And CO2 also affects wetland methane emissions, and there is of course a link of both carbon and methane emissions from permafrost thawing, which is related to either the CO2 impact on climate or the methane impact on climate. So warming is bad news for permafrost in any case. On the methane side, you have methane affecting wetlands as well. So you have diffusive fluxes with methane. So if you imagine that you increased methane in the atmosphere, and just like the ocean atmosphere exchange, the partial pressure of CO2 in the air and in the water is going to be a key factor in determining the fluxes, and the same thing can happen on the wetland methane emissions. Both of them, of course, affect temperature, and temperature affects permafrost as well as wetland distributions and methane emissions. So this is a feedback that's included in some models, as we saw, and an example of their forecasts or projections into the future, with all their uncertainties, with some models explicitly including wetland dynamics and rice paddies, and some including livestock mechanisms and so on. But when you make projections, there is assumptions made in the scenarios for the future on each of those. How much rice will be produced based on population projections and so on. So there are always additional uncertainties that can be added depending on how we do it. Methane emissions have had some variability on interannual and secular trend timescales. You can see the seasonal cycle in methane as well, similar to the CO2 seasonal cycle we are used to seeing in the Keeling curve. But this article from just last year, well, now it's 21, so from 2019, talks about Earth's methane emissions are again rising, and we don't have a very good handle on the sources or the reduction in sinks. Why is this happening? There was a flattening here for a while, and this is again in parts per billion that we have to remember. obviously there are lots of efforts to monitor methane, especially for a country like India, which has lots of cattle, lots of rice paddies, and some wetlands and so on. As a part of their commitment to the nationally determined contributions under Paris Agreement, they have to track their methane and they have to provide a budget. Okay, so that's kind of the methane story in terms of its sources, its life cycle, its interactions with climate, climate impact on methane, climate-carbon interactions. Since we're talking so much about vegetation, another piece of the puzzle has to be added here, especially considering that things like planting 1 trillion trees are being proposed as solutions to climate change, and we have already talked about the caveats that have to be associated with those in terms of how long forests can continue to take up carbon dioxide, and what happens when there are wildfires, and how climate change itself is going to affect the forests above ground, biomass, carbon emissions, and so on, right? So isoprenes are these biogenic volatile organic carbons, VOCs as they're called, emitted by trees and of various forms. So here you have crop emissions, soils taking up some isoprenes, trees, shrubs, animals and humans. We have grasses and forbs. Forbs are basically vascular plant without significant above ground woody tissue, and it's not a grass, a sedge or a rush. So it's a kind of a functional type that sits somewhere in the middle, and of course mosses. And there are atmospheric reactions with isoprenes coming from the ocean and land overall that determine the isoprene cycle. What is critical about it is that if you look at the average flux between 2005 and 2016 in molecules per centimeter squared per second, so these are the biogenic VOCs that I mentioned, isoprene reacts with oxidized molecules that would otherwise react with methane, which means the methane loss term is diminished, so the residence time of methane is going to be longer. Remember, the average lifetime is 12 years, but if it is burned off or converted to something else by reactions, and those required radicals are taken away by isoprene, then the methane life cycle is going to be affected. And again, methane is a high global warming potential gas, so it's going to enhance global warming. So that's kind of an indirect effect. Isoprenes also react with nitrogen oxides like nitrous oxide, and that leads to creation of tropospheric ozone by photolysis, which is the reaction because of sunlight, driven by sunlight. And there are also dimethyl sulfide that can be created, and DMS is typically considered to provide cloud condensation nuclei. Okay, so if clouds are formed, enhanced cloud formation happens because of DMS related to isoprene, then you can have a cooling effect. But the tropospheric ozone produced by reaction of isoprenes with nitrogen oxides is again a greenhouse gas with high global warming potential, as well as it's deadly for human health. And we talked about how it actually can reduce crop yields. Okay, so most isoprenes released into the atmosphere are by terrestrial plants. There is now more and more evidence that marine environment is also producing isoprenes, especially in coastal zones and temperate estuaries. This is a schematic of the feedbacks now, with the ecosystem carbon cycle on this side and atmospheric chemistry on this side, with isoprene being an agent in the cycle. So we already talked about CO2 interactions with vegetation in terms of fertilization and the fluxes, so sink and source, and of course CO2 affects temperature, and with its effect on vegetation and ocean, CO2 is going to affect isoprenes as well. And we talked about the nitrogen oxide reactions leading to ozone formation, OH radical affecting methane residence times, and these are secondary organic aerosols that are also going to be affected by isoprene, obviously, which again affect temperature depending on whether they are scattering or absorbing. Okay, so vegetation affects methane directly as well, and methane affects temperature directly as well. Ozone affects temperature as well. So we are again talking about very complicated interactions between climate, carbon dioxide, methane, isoprene, vegetation, and so on. We will come to vegetation-atmosphere interaction models in the context of wildfires, but I'm going to stop this here and continue on the methane, CO2, and the Arctic in the next podcast. Again, survey of feedbacks that we are aware of. We understand many of the processes. The trick is to model them accurately, validate them, calibrate them so that they are included in the future projections to have the full Earth system feedbacks.